That means the lower limit of the detectable Raman line. So if this is very nice, then we can measure low frequency Raman. But typically, this is not so. Typically, cutoff maybe 200 wave number or so. So if we want to measure the low frequency Raman, another element is necessary. But 200 wave number is enough low for daily use or typical use.
So starting up, there is a need of signal correction. So what is the need of signal correction? And in one only, like upright position and if the light is coming from the upright or the downside. You explained the signal correction in one of them only.
Signal correction is done by these optics. So this microscope objective focuses the light onto samples, so very small spot be illuminated. And the scattered light is also collected by this.
But no. Why there is a need of signal correction? Because we want all the scattered light to go through this pathway, like to the dichroic mirror. Then eventually it will separate the Raman and the remaining light. Why there is a need of signal correction at this point?
I mean, you want to deliver all the signal into detector.
Yeah, because mirror will work there, no? It will separate the desired light. It will go to the detector. Why there is need there only we are correcting this?
You mean scattered light goes everywhere, but only detecting the upper half? It's a good question. There is almost no optical element that enables the correction of entire solid angle.
That's why we are focusing on like a single plane. That's why we are doing signal correction in the start only.
Right.
So that the maximum amount of light or the different wavelength of light can pass through this system.
Any other question?
So one more question. To explain that we are using CCD detector. Apart from this CCD, we can use other type of detector. And what is the advantage of using CCD in this particular?
So CCD is the first choice in this kind of instrument. So CCD, advantage of CCD is that detector array or the two-dimensional array of the detecting element is gathered. Instead of this, we can use single channel detector. But in this case, only one wavelength is detected. So we need to scan next.
It will take
more time, right?
No. And it can do simultaneously different areas.
Right.
So, what's the full form of CCD? Full form of CCD?
And charge coupled device. Any other question?
So, is there any need of sample for strong Raman signal between the larger sample area and small sample area?
Large sample area and small sample area.
Yeah. My question is there any effect of area of sample to getting a strong Raman signal?
Okay. I derived some formulation about Raman intensity. And Raman intensity, I Raman is in proportion to I0. If we introduce stronger excitation beam, then the Raman scattering should be stronger. And laser output power is constant. If we focus the laser power in this size, density is certain value. If we focus on smaller area, density becomes larger, and getting smaller, density is much larger. Then I0 becomes much larger. Accordingly, I Raman gets larger. So if we want to get a strong signal, smaller focal point is more advantageous. But at the same time, it easily damages the sample. Okay, stronger light damages the sample. So it depends. In the case of semiconductor or some hard material, it's possible to focus on it is safe. When we want to measure skin or some living cells, strong signal and it will be burned, becomes carbon. Okay, so it depends on the purpose and highest laser power or smallest focal point is limited by the condition of the sample. Okay.
It may vary from like if the thickness of the sample is large or like small, it is very thin or it is very thick, it will also affect the intensity of the Raman spectrum.
Actually, I can say Raman signal is generated from the focal point. If we see the top, it looks focal point, but if we see 3D, then it's focal volume. So if the sample is extremely thin, only the limited part of the focal volume is used. If the sample is thick enough, the focal volume is all covered by the sample. In that sense, extremely thin sample does not give strong signal, and so some thickness is preferable. Any other question? No, shall we move to measurement?
So here we can do for liquid sample. There is two types of instruments. So we can just drop the sample on the slide and take the measurement, or we can take the sample in the cuvette and so here we can put the cuvette and which one will be better.
Just a moment. I brought capillary glass. Okay. Just a moment. Excuse me. So when we measure the solid sample, we can put on the slide glass and focus the laser spot on the glass. But today's sample is the same with yesterday's. This is a sugar solution, right? In this case, we need a container, glass container. Then he suggested one method is to put a liquid on the glass plate and measure as it is. Okay, in a short time, it's stable. It's okay. But if we want to accumulate 1 hour, it evaporates. Okay, water disappears and solid sugar remains. So it's not preferable. Or another method is to use a cuvette. Then there is an attachment. So we can put the cuvette here. That is another method. This is effective. One problem is that we need much volume. So if this is the sugar solution, it's okay. I can purchase sucrose in the market. If this is a protein sample, say 1 milligram, 100 US dollar or something, then such a volume is very difficult to prepare. So precious sample is usually very obtained very limited volume rate. So it's preferable if we can measure is a smaller volume. Then I brought capillary glass. This is a glass tube. Okay, you touch. Not very, not no special one. So capillary glass. Then put one drop and tap and move to the bottom.
First water or direct?
First water. Right. If you fix here, then the stroke is short. You should. Okay. It has gone somewhere. So. It is difficult than I expected. How can I do?
So you can use syringe.
No, syringe is.
Syringe. Do
Shall we use this? Shall we use this one? It's okay. Okay, shall we measure this part? Okay.
So I don't know how to with this.
Ah.
So, okay, just placing the sample there. Okay. So,
Okay, irrespective of the sample preparation or setting, we put on the microscope stage. Okay. Then we will see where is a sample by checking a physical image.
this is the surface.
Hmm?
This is the surface.
What is the working distance of this one? Okay, let's use your method. Okay. Let's use.
No problem. It will be okay. Actually, maybe this is the sample.
Probably this is okay, by scanning stage we see some bright part. So this is a glass surface probably. You see?
We'll go inside.
So by checking the Raman signal, we can distinguish glass and water.
So what will be the measuring range? So from 100 to 4000. Accumulation time.
typical value 9 or 10 or second or so first of all let's check the appropriate height.
Just 633 at 600 rating. 2 rating are available. 600 and 1800. So
800, 600 and
600.
broader.
Yeah. 600 and 633 100% power, laser power.
Yeah. Okay, now the accumulation data sampling is started, but you know, sample volume, focal volume is very small, and sample is relatively large. So we need to focus on water, not the surface glass. So we should check the spectrum. Then we can distinguish glass spectrum and water spectrum. Okay, still it looks like glass.
Grass.
So in this case, we should approach the focal point closer. This is water is here. No, water is 16, 40, 40. Okay, so in this setup, four regions are separately measured and connected. And at every, so first region, second region, third region, fourth region. Okay, then accumulation is 7 times for each region. So this is a OH stretching band. Okay. So next time, let's set accumulation 1. So what we need to do is to set the focal point in the appropriate point. And this is not easy because the focal point is small. Okay, so we are looking for good point in 3D volume. Already water is here. Still continue.
So should we set the region between 2800 to 4000 to check the focal point?
This region.
Accumulation 1.
Yes. You see now the result is dominated by sharp spike. This is typically due to cosmic ray. So some energy particle comes from sun or somewhere space, and it goes through the CCD detector. Then strong signal appears.
Can you check
Hmm.
this?
Aha, this is good. Right, right?
A little bit more.
No signal. No signal. Then, let's make it open. So put okay. It's easier. I see. So now the new attachment is put here. And instead of the microscope objective, it focus and transfers the light onto this cuvette. So this is a typical Raman measurement. So not a Raman microscope. This is a typical Raman measurement. And we can put the sample here.
Sir, can you explain again what is that thing?
Okay.
Which is
Could you come? So this is an attachment. So light is typically passes through the microscope objective and focus on small spot. But this is not a microscope objective. Light is transferred to left, irradiate. There must be a mirror. There is a mirror. And this is a typical Raman measurement. Again, this spike is cosmic ray and appears only once, so by averaging it disappears. Okay, then now the focus is okay, so let's expand the region.
So they stop it now? From 1000 or 200?
500. Okay, now the exposure time is 6 seconds for each scan, and 4 spectra are averaged. And this is OH bending. This is OH stretching. You may remember yesterday FTIR measurement. It was much clearer and less noisy. That is the signal spectrum of H2O. But IR absorption band of H2O is huge. And this is relatively smaller. So this is why Raman spectroscopy is more advantageous for aqueous sample measurement. Okay.
So they change it with spectral solution?
Okay, would you save this data?
Yeah. So in this way, or we can do the baseline correction here only. So should we do the baseline correction?
As it is.
As it is. And
Then move scroll solution. Let's move to the next sample. Excuse me. Excuse me. Excuse me. Sorry, overseer. Excuse me again. I could see.
Yes, sir, you can write it. Accommodation, same. Everything
Same,
is
same. Okay. Will you save the data? Not yet.
Should I give you the data?
Okay, at a glance, we find the new peaks in the measurement of the sucrose in water solution, right? So like we did it yesterday, let's do the data analysis. This is text data.
Yeah, text.
Oh. Okay, so today's data is just a moment. Close. Okay, so this is the result obtained today. So black is the water spectrum. So yesterday we detected the OH stretching as a transmittance here. That corresponds to this large peak, right? Then OH bending is here, HOH bending here, and it is much smaller than yesterday. Then red spectrum is a scroll solution. We found CH stretching here, and it appears here. Okay, close up. So CH appears here. And yesterday we found probably CO stretching here, and this is the largest. But in the Raman spectrum, still the SN ratio is not good, but we find 2 peaks, 1 peak, and multiple peaks. And more importantly, appearance is quite different. Okay, it may be clearer. Peak here, peak here, peak here. So we can compare the IR and Raman spectra, and they give us different information. So it depends on the purpose. If possible, please measure both and consider the peak assignment. And just a moment, I change the spectral region. Okay, it may be clearer. Okay, so the signal count is now 20 or 30 count. When we prepare the figure for the publication, we need to collect 1 million count to ensure good SN ratio. So now the measurement time is 6 seconds multiplied by 4 times, so nearly 30 seconds, 24 seconds, and we get this data. And that is, we need to spend more time to get better data. Then we can identify what is the peak position, what is the intensity, what is the bandwidth more clearly. Okay. So this is the first group. So we cannot compare two sugars, but this is the result Raman spectrum of sucrose. Okay. Is there any question?
So, in order to decrease the noise, we need to increase the acquisition time and decrease the accumulation time.
Just a moment. Partly, yes. So if the time is infinite, then we can increase both exposure time and accumulation number both. If the time is finite, then we should increase the exposure time as long as possible and decrease the accumulation number. It's because one of the origin of the noise is the AD conversion noise. Okay, Raman spectrum or intensity pattern of the Raman scattering must be continuous. But continuous number cannot be understood by PC. That is, continuous spectrum is detected by CCD, and at that time, CCD will judge this intensity is count 1. This intensity is count 2. This intensity is count 3. Okay, how about 1.5? Okay, 1.5. Okay, 1. So it digitizes the continuous number to digit number. At that time, error occurs. So in principle, it should be continuous. So if the measurement count is small, that kind of analog to digital conversion noise becomes prominent. So to avoid such a situation, we should accumulate signal count, and maximum is 10 to 16th power, 65,000, around 65,000. If we reach to the signal intensity close to 65,000, then that kind of AD conversion noise becomes less prominent.
Sir, if we increase the accumulation time, it means the number of time it is recording one spectra will be increased. So it will be difficult to analyze that data now. If we are seeing more number of peaks, if the accumulation number is increasing, it will be difficult when we are trying to see, like, interpret our result.
My explanation is about the exposure time and accumulation number. So if you set the exposure time short and increase the accumulation number, then the AD conversion noise increases. So instead, you should set longer exposure time and correspondingly smaller accumulation number. It's better. But if you have a time longer the exposure time and increase the accumulation number, it's the best.
Increasing both.
Both is the best if you have a time.
Do depend on the sample as well. Like these two parameters will also be affected by the type of sample.
In the case, photo damaging is significant. Then
we need to decrease the
exposure
acquisition
time. Total acquisition time. Time to
next batch.
So can I just take a photo?
For next batch, should we do the same?
the same. It was confusing. Sorry.
So We are not using it, so that's why maybe it's problem. We are not using this one,
I
so
see.
that's why maybe. सब लोग आ रहे हैं हाँ हाँ
Okay. For Okay, shall we start? Okay, so this is a Raman spectrometer, Raman microscope. Okay, the name is Ram HR High Resolution Evolution. This is the product of Horiba, Japanese company. Okay, then in order to measure the Raman spectrum, we need excitation laser and sample cell, and we need to collect the scattered light and deliver to monochrometer. Then plating disperses the mixed color into each color. Then we detect the Raman signal. Okay, so everything is in this box. So over there is the excitation laser beam. From left 532 green laser, middle is 633 red laser, and right is 785 red laser. Okay. When the laser light comes into our naked eye, then it damages the eye, and it's very hazardous. So for safety, the laser beam goes through the optical fiber and it is introduced into this equipment. Probably you see over there. So laser beam comes into this box. And sample point is here. When we measure the Raman spectrum, typically we irradiate the sample cell from the bottom and gather the Raman signal at the 90 degree. This is 90 degree scattering configuration. Why 90 degrees good? If we catch the signal from this side, then strong laser line directly irradiates the detector. So it's not a good idea to detect Raman laser strong line. So if we put the lens at 90 degree, laser goes straight and Raman scattering goes everywhere. So the content of the Raman signal increases, it's advantageous. Still there is a Rayleigh scattering, and so laser beam, the wavelength of the laser beam still remains, but weaker. So usually we choose 90 degree scattering configuration. How about in this case? This is a Raman microscope. So here is a microscope objective. Laser line comes from the top of the microscope objective, and this microscope objective focuses the light onto small spot. Then small spot irradiates the surface of the sample. Then the Raman scattering occurs from this small spot to everywhere. In this microscope case, this objective lens serves as a focus lens as well as signal collection lens. So the scattered light is collected by this lens and delivered to upward. So the laser beam comes from the top and signal goes returns the same route. In this sense, this is a backscattering configuration. Okay. But anyway, this is very convenient too because the laser focus can be very small. I explained the Raman intensity. Raman is in proportion to I0 incident laser power. So laser power is already fixed by that laser output. If we focus the laser beam in this area, the density of the photon is certain value. If we focus the laser onto smaller spot, density increases. Further decrease, and the photon density becomes much larger. Accordingly, the Raman signal becomes much larger. So in that sense, tight focus is advantageous to get a larger Raman signal. But we must know strong laser beam can damage the sample. So if the sample is a solid material, such as semiconductor, it would be okay. But if we want to study the status of skin or living cell, strong laser makes it carbon burn. So in such a case, we should lower laser power to keep laser photon density low. Accordingly, we cannot increase the Raman intensity so much. But anyway, smaller the spot, signal is higher, so it's good. Okay. Then back scattering comes back to the box. Laser line excitation beam comes from this side, and Raman signal, including Raman signal, goes back. How can they separate it? We put one optical element here. That is dichroic mirror, two-color mirror. Two-color mirror. When I express a spectrum, then vertical axis is the transmittance, horizontal axis wavelength. Then transmittance is 100, 100, 100, 100, and suddenly becomes 0, 0, 0, 0. Then reflectance is accordingly 0, 0, 0, 0, and suddenly 100%. So the center is a cut-off wavelength. So this element is transparent below cut-off wavelength and serves as a mirror above cut-off wavelength. Then let's put this element here. 633 comes, and this is transparent for 633. So it passes through and focuses onto sample. Then backscattering component, including Raman signal, comes here. Then for 633, it is transparent, so daily line goes straight. But for the Raman signals, it is mirror because it is above cut-off wavelength. So Raman signal is reflected and go into the monochrome. So this is the optical element that separates 633 and Raman signals. I guess one more filter should be here, not bandpass filter or non-filter should be here to remove the, not filter, to remove the excitation wavelengths to make the efficiency higher. But anyway, by separating the Raman signal from the excitation laser beam, the mixed Raman signal is introduced into the monochrometer. Then monochrometer includes the grating. Then grating separates the mixed color into each wavelength. Then separated wavelength is detected by this CCD detector. CCD is the abbreviation of the charge-coupled device that converts photon into electron. So the conversion efficiency is less than 100%. So the best value may be 80 or 85%. So not 100%. But anyway, it's high enough to convert photon information about to the electron information. Then accumulated charge is counted and transferred to PC, and it appears as a intensity at each wavelength. This is spectrum. Okay. Is there any question? Is there? No.
Sir, why the efficiency of CCD detector is less than 100%?
I don't know. I have no idea. So please ask the company. They try to make it improve. But for example, on the surface of the detector, some reflection occurs. So some anti-reflection coating is put to make the throughput higher. And I'm not sure. Yes.
Sir, I have a question. Can you explain more about backscattering? How it is happening? It is going to a particular direction. The scattered light is going to in a particular direction. If a light falls on a sample, light will scatter in all directions. So how it is going to a particular direction in the backscattering?
So in principle, Raman scattering occurs for all the directions. If we detect from the side, this is a 90-degree configuration. If we collect a signal from top, this is backscattering configuration. So there is no difference. It depends only on the numerical aperture of these optics. So if this optics can gather larger solid angle signal from the larger solid angle, then the signal count becomes larger. If this is small lens, only gather small solid angle, then less efficient. So it does not, it's the same, this direction, this direction.
Some amount of light must be lost in other direction. The scattering light, those are in other direction, except 90 degree. That are getting lost now.
Right?
That are getting lost. So that will decrease the intensity of the Raman signal.
Difference of the intensity of the Raman signal between two configurations? In principle, it's the same as far as the numerical aperture is the same. But a good point of this configuration is that once the focal point is fixed, then the correction position of the lens is automatically fixed to the appropriate position to correct the signal. So in the case of 90-degree scattering, we need to focus the laser onto one point by tuning this lens. And also we need to set this optics to the appropriate position. So we need two optics. In this setup, only one element is used. So always good point for the excitation is good point for the signal correction. So in that sense, this is advantageous. Any other?
How scattered rays are collected from the sample?
Sorry? How?
How scattered rays are collected from the sample whenever we start the
Sample is? Sorry.
when we start the experiment for collecting level spectra, first it's based on scattering of light. So how can we analyze how much amount of radiations are scattered from the sample?
So, in this setup, all the signals comes from the focal point. So, no other point. So, all the detected signal comes from the sample. If the focal point is far from good point, then it comes from air. So, nothing.
From where sample is loaded? Sample is loaded from where?
Sample is typically here on the microscope stage, and XYZ position of the sample is tuned fine. Then we find good position. And one more thing I explain for this time is that in today's experiment, we use some attachment. So exactly speaking, today's measurement is not a Raman microscope measurement. So you see, here is an attachment, and laser beams comes from the top, and it is reflected by this mirror and focal, passing through the focal lens. It is focused on cuvette, and the Raman scattering from the cuvette is collected, and so this is also the back scattering. It is collected, transferred to dichroic mirror and transferred to the monochrometer. So it facilitates measurement of the liquid sample. Okay, today's sample is in cuvette.
So how we prepare the sample? Like if there is solid or the gaseous material, then how we will prepare the sample?
How? So generally speaking, in this case, dissolve the sugar in the water, and this is sample. One important point is that we need to use pure material. So the biggest problem is the fluorescence. So if there is impurity, it gives a fluorescence and makes the quality of the data lower.
So can we take the spectra of gaseous molecule?
So by preparing some container, glassware, and fill the gas. But gas density of the gas molecule is very low. So typically they prepare container for the high pressure and increase the pressure and measure the Raman spectrum. By doing so, we can increase the density of the gas molecule, and Raman scattering signal becomes larger.
How can we study biological molecules if laser damages it?
Yep. So when we put the cell or living specimen at this point, then the laser power becomes too strong and burning. So to avoid such a situation, we lower the laser power. That's all we can do. Lower the laser power. So typically we use 100 milliwatt or so for the measurement of the organic solvent. But in the case of living sample, 1 milliwatt, 2 milliwatt, very weak laser power is focused on tightly focused on leading cell. Then we can achieve spatial resolution because the spot is small. So we can scan each point and avoid damage. So reduce the laser power is one and only one method to avoid.
Like we used to do in UV spectrophotometer, and we have to set a baseline correction. Do we need to do it here again?
Baseline correction. As necessary. So there are many reasons to affect the baseline. For example, room light or some display light. So by turning off all the stray light, shutting all the stray light, and do the experiment carefully, then the baseline becomes lower and lower. And ideally it should be flat. But that's it.
From this machine can be with all type of Raman spectra, either it may convective, either it may seals surface enhanced Raman. Can you measure all type of Raman from that?
Must be possible. So the surface enhanced Raman is achieved by adding the nanoparticle into the liquid sample, but probably some steering is necessary. Any other question?
ASN RPC is used to study fingerprint.
AS
ASN RPC. Used to study fingerprint, then we have to set a baseline now to detect oil.
Sorry, RSR.
ASN RPC.
It's not generalized term. It's not used everywhere.
Some types of nanoparticle, composite nanoparticles, some composite nanoparticles, silver colored nanoparticles.
Probably by adding some fabrication at the sample point, additional experiment would be possible. But at present, it may not be possible. So it depends on. So the instruments should be customized for your purpose. Okay, shall we move to the measurement?
Yes.
Okay. Then already we measured the water, so let's go to
Water again or not?
no.
So fructose.
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 This is
Water.
sucrose.
This is water. I
Water.
have changed it.
Okay. Then let's start
Water.
from water. So we do the two experiments. One is solvent water. The other is sugar solution. Okay, now we are measuring water. And do you remember yesterday we measured the FTIR spectrum of water? At that time, we detected OH stretching band and HOH bending band. This is a HOH bending band. And this is OH stretching band. Okay? I hope you remember yesterday's data. So black is water. Okay, so this is a negative peak transmission spectrum and OH stretching, and this was HOH bending, and it was very clear. Now you see, it is smaller than, much smaller than this peak. It was nearly 1/3 of the intensity, but this is 1/10 or less. So this is why the Raman spectroscopy is more suitable for the measurement of the biological samples in aqueous solution.
Students are
Can you again repeat? Can you please explain again?
Experiment.
Yes, sir.
Explanation.
Yes, sir.
So yesterday, do you remember black spectrum is a water spectrum. Then OH stretching of H2O is here. HOH bending is here. And this is intensity is 1/3 or something. So this is large peak. And in this case, in the case of Raman spectrum, this is strong, but HOH bending is quite weak.
Why, sir?
Hmm?
Why?
So please ask water. So
What the bigger peak indicates? The bigger peak.
OH stretching. So the Raman intensity.
Sharp one. The sharp one.
This is
This.
this is I should explain. This sharp peak I explained. The vibrational band of the liquid sample should have certain width, and this is extremely sharp. So we should not regard this is a real vibration band. If this is a vibration band, it means vibration continues long time. So we can define the frequency uniquely. Instead, this is not a vibration band. So in the space, there is a particle flying from the sun or somewhere, and such a high energy particle passes through the CCD plate by chance. Then it passes through only one pixel of the CCD detector array. Then it is detected as a sharp peak at only one point. This is so-called cosmic ray. Cosmic ray. So the heavy energy particle flying space. So in this is the noise, and it disturbs the data analysis. So we need to remove this peak.
Sir, is it okay if such peak exists in the final data while sending for publications?
No. So during the data analysis,
You have to repeat the experiment.
so by accumulating, by repeating the same experiment, so by increasing accumulation number and make it very steep.
How can we analyze these type of spectra?
This is measured by the digital camera. So you may refer to some publication. A friend Nomoto-kun prepared that paper. So put a grating and set the digital camera instead of CCD detector, and it's possible to record.
This is your taking photos.
Thank you.
Everything is same.
Sir, how to know the sample is well focused?
In this case, focus on the chip.
For here we can see na, the sample, the laser light is in the focus. While doing solid sample, if we use glass slide, we have to focus the laser light into the sample,
Right.
and from here we can also see na, the sample is focused or not.
It's possible
How
by
to know that the sample is well focused?
So there is a button to show the visible image.
What is the function of this now? This now. What is the function of this now?
By changing X, Y, Z and focal length.
Focus the sample.
So initially the image is very broad, and it becomes clear. 1 point.
So all the time, why it is coming in this position only?
This?
All the time it is coming
Now
at
I'm
this
thinking
position.
it may be some defect.
It may vary, the position may vary, na? But all the time it is coming at that position.
In the previous measurement also.
There is some problem in the detector.
Right. So it happens. Okay, then let's see the result. Okay, so for this time we measure the fructose, and it gives a green spectrum. Black spectrum is water solvent. Then its obvious difference is here, and many peaks appear, right? Then solvent is subtracted from solution spectrum. So this spectrum gives the information of the solute, fructose. So pink is a fructose spectrum. Yesterday we found in the fructose spectrum that CH stretching appears below 3000 and corresponding peak appears here below 3000. There is a CH stretching. As well as this peak, we find many peaks below 1500. Blue is the scroll spectrum. SN ratio is a little bit not good, but anyway, we see intensity pattern is different, peak position is quite different. Okay, as we saw yesterday, each sugar gives a different intensity pattern, spectral pattern. And yesterday's data, the difference was gathered near 1000 wave number. But in the case of Raman spectrum, difference appears in this region, below 1500 wave number region. Okay, so let's change the range. Then we see clear difference between sucrose and fructose. So, these two peaks. No. Yesterday I put this peak position of these two peaks. Now expanded. Okay, so there is a clear difference between sucrose and fructose spectrum. So it's easier to distinguish these two similar sugars. Okay. Now the signal count is nearly 50 count. So when we prepare figure to publish the paper, we gather 1 million count or so. Okay, this data is obtained by 24 seconds, 4-second exposure, 6-second exposure, 4 times medium accumulation, 24 seconds. Okay, and already we can distinguish difference these two sugars, but please be patient for a few hours to get better spectrum. Then we can discuss what is the peak position, what is the bandwidth, what is the intensity. Then under which condition it changes. At present, even if you insist it moves one wave number, okay, SN ratio is poor, so you cannot say in that way. But if the SN ratio is 1000 times better, then one wave number shift will be clearly detected by calculating different spectra. So the first priority to get a good spectrum, then do the good data analysis. Then we can get much information from the spectrum.
This can also show the number of scan data. Number of scan, how much time?
6-second exposure and 4 times accumulation. 24 seconds. Okay, already this is good enough to distinguish. So it depends on the purpose. If we want to distinguish which was fructose, which was glucose, I want to add fructose to my cooking, then it's easy to use Raman spectrometer to identify which is fructose.
So one thing is that when we want to take a Raman imaging spectra, so can direct how this can be achieved. Raman imaging spectra, if we want to see that in APIs, tablet, how can we see?
Imaging, if you do the imaging, then you can gather this kind of data at each position. Then you may plot the intensity at certain wave number or to make a 2D image, or you may fit some model spectrum to estimate amount of that compound and plot the coefficient to make one two-dimensional image. Or there are various ways to make image data from bunch of the spectrum.
So can two different compounds can make the same peak?
Sorry?
So can two different compounds can make the same peak? And how can we only observing the peak we can distinguish that a particular compound is making this peak?
So if the molecular structure is different, vibrational mode is different, then the frequency becomes different. So the peak position is different. So there is no two different compounds that gives exactly the same peak intensity pattern. So it's unique. That's why we call it fingerprint.
So if we get the peak, we have to check our original data to match that the particular compound is present there.
So if you want to know what is here, then you should check the model spectrum, record the model spectrum of the pure compound, then compare. If you know there is only one compound, then discussion is easy. If there is two compounds, then the identification becomes more complicated.
So if a solution contains two or more compounds, how can we distinguish?
So compare with the model spectrum. So prepare the model spectrum in the solution for several model compounds and list all the spectrum and compare. This peak may be attributed to this compound. In that case, another peak should appear at this position. If that is present, it becomes more plausible. If that expected peak is absent, then that assignment is wrong. So by comparing between the unknown spectrum and the model spectrum, you will see what is here.
What is the significance of Raman shift in measuring the spectra? Raman shift.
Raman shift is
Unlike chemical shift in NMR we use. So what kind of includes that?
Raman shift is the difference energy difference from the excitation laser. Significance. So always we need to calculate the Raman shift or energy difference from the daily line. That is always it's a horizontal axis.
Excuse me. How would the spectrum change if we use different lasers?
In principle, it should be the same as far as it is a non-resonant condition. But if there is some absorption, then some resonance effect start to appear. Then the intensity of the some chrome 4 band becomes more intense. Then the intensity pattern becomes different.
So difference between elastic and inelastic scattering. Can we see that what's inelastic scattering, what's an elastic scattering?
Inelastic scattering, like neutron scattering.
Sir, can we observe elastic and inelastic scattering in the graph?
I have no idea. Anyway, this is a scattered light spectrum, and origin should be identified in separate way.
Sir, I have a question. If we have blood and
Blood.
sir, if we have blood sample and we have another sample containing water, iron and oxygen in same ratio as blood, do the both makes the same graph? Both the sample?
Including water or not.
Yes, sir.
Then the concentration becomes different. So by setting the OH stretching as a standard of the water signal, then intensity becomes slightly different. So after dilution, intensity becomes smaller. To identify that difference, you need to make SN ratio much better. For now, 50% difference dilution could be identified, but 1% impossible.
So how can we selectively analyze the hemoglobin portion of blood content?
So by choosing the excitation wavelengths to resonate to the heme group, then the intensity gives a hint. Okay.
So to get the concentration, do we need to observe the graph and put it in Beer-Lambert's law to know the concentration of any particular compound? Do we need to observe the graph and put it on Beer-Lambert's law?
Put it on. You have a sample and
इसमें रेफरेंस कंपाउंड चाहिए होता है रमन जैसे टीएमएस यूज करते हैं एनएमआर में इसमें कुछ रेफरेंस सैंपल होता है
Reference is no reference. It's standardized. Standard sample generally used to calculate the instrument. There's no reference sample. Reference is only the excitation source. The excitation source, that is 532 nanometer is the excitation source. Then with reference to its excitation source, there is a shift of
reference
stocks.
Yes, sir.
any other question?
Sir, how are you separating the Rayleigh scattering?
So by putting dichroic mirror and filter, and it shuts Rayleigh line, it affects the measurement very difficult, so we remove it.
Sir, in your slides you mentioned that there is two type of filter. One is a notch filter and has a gags grating filter. So what is the difference between these two filters?
So principle is quite different. So In the case of notch filters, the dielectric medium is layered. Multiple layer of the dielectric medium is put on the surface. And in the case of black notch filter, it's a grating. So the principle is quite different. Okay. And shall we finish?
Doppler and collision broadening effect, how can it measured? Doppler and Doppler broadening, how can we see?
Doppler broadening.
Collisional and Doppler.
I'm not sure about the gas phase spectroscopy. Sorry. Okay, then shall we finish? Okay.
I'm sorry, could you just please tell me the pathway of the laser once more? The pathway of the laser once